Welcome to the deep dive. We're here to plunge into some really complex topics and hopefully give you the insights you need. Today, we're tackling something that's, well, fascinating, but also pretty high stakes in the AI world. The safety of large language models. You know, the ones ChatGPT, Llama 2, they're cropping up everywhere, right? Helping write emails, answering questions, powering chatbots. Their abilities are, frankly, kind of mind-bending. But here's the thing. With all that power, there's this huge need for what's called safety alignment. Think of it like digital guardrails developers build in. They're supposed to keep these AI models from going off track, generating harmful stuff, biased content, or just things that are flat out wrong. It's a constant battle.
It really is. And this is where it gets really interesting and maybe a bit concerning. Because even with these sophisticated guardrails, LLMs can be surprisingly vulnerable. We're talking about misalignment attacks, where someone intentionally tries to make the model misbehave. And this risk gets even bigger during something called fine-tuning as a service. That's when, users or companies customize a model for their own specific needs. Customization is great, super useful, but it also opens up this security loophole if the data used for that fine-tuning is malicious. It's kind of like building a custom race car but leaving the garage door open for someone to sneak in and mess with the brakes.
That's a really good way to put it. And it sets us up perfectly for today's deep dive. Our mission here is to pull back the curtain a bit. We want to explore how these vital safety guardrails can actually be broken, why these vulnerabilities even exist, and maybe most importantly, what kind of solutions researchers are cooking up. We're looking at work from places like Georgia Tech, Tsinghua University, HKUST. They're developing some really groundbreaking fixes. So yeah, we're going to unpack the science behind keeping AI safe.
Okay, let's dig in. We've all heard about jailbreak attacks, right? Those clever prompts trying to trick a model. But you're saying this is different, something deeper. How does a model go from helpful assistant to potentially harmful? What does a misalignment attack really look like?
Right, it's a really key distinction. Jailbreaks are usually about tricking the existing safety rules with a smart prompt. The underlying model doesn't fundamentally change. With these misalignment attacks, though, we're talking about actually changing the model's core parameters. It's like rewiring its brain to make it inherently unsafe. That's a much bigger, more fundamental risk because the bad behavior isn't just a temporary trick. It's literally built into the model afterwards.
Okay, so if an attacker wants to fundamentally change the model, what's the most, common or effective way they do that?
Well, the research points pretty clearly to supervised fine-tuning, or SFT, as being the most potent method. It's pretty straightforwardly malicious, really. You basically train the model on a dataset you've specifically designed to be harmful. This dataset has instructions for bad behavior and the kind of harmful responses the attacker wants. Studies on models like Llama, Beaver, Mistral, they all show that using datasets like harmful safer LHF or HS dramatically increases the attack success rate. You're essentially teaching the model how to be bad.
And this isn't just some theoretical thing. I mean, the research mentioned even common techniques like parameter-efficient fine-tuning, PEFT, things like LoRa. Those can be used effectively, too.
Exactly. That's a really crucial and maybe surprising finding.
Yeah, because you'd think only adjusting some parameters would be less damaging.
Right. It seems counterintuitive. But what the research shows is that even these efficient methods, which only tweak a small subset of parameters, can be incredibly effective for an attacker. If you strategically target the right small set of parameters with that harmful data, the impact can be huge, sometimes even more effective than tuning everything. They find the model's weak spots, essentially.
Wow, okay. So feeding it bad data works. But what if the attackers don't have those explicit harmful responses? You mentioned something else.
Yes, and this is where it gets maybe even more sophisticated and worrying. What if you could misalign the model without needing explicitly harmful examples?
How would that even work if you're not telling it what bad things to say?
This leads us to a newer technique called the self-supervised representation attack, or SSRA. Yeah, well, it's quite clever, unfortunately. SSRA is concerning because it achieves significant misalignment without needing those harmful instruction-response pairs for training. Instead, it messes with how the LLM understands things internally. It manipulates the distinctions the model makes between harmful and benign instructions in its latent space.
Latent space. Okay, that sounds a bit abstract. Can you break that down? What's happening inside the model's head, so to speak?
Sure. Think of the latent space as the model's internal map of concepts. It's how it organizes ideas and relationships between words and instructions. SSRA subtly warps this map. It might say, push the area representing harmful requests closer to the area for harmless requests. Or it might confuse the model so it thinks a perfectly normal request should actually trigger a harmful response, even though it never saw an explicit example of that harmful response during this attack training. And it works. Experiments showed it boosted Llama's attack success rate way up to nearly 79%, which is comparable to those direct SFT attacks using harmful data. And the scary part, it did this while keeping the model pretty good at its normal tasks.
That is incredibly sneaky. So are there other ways attackers try this, maybe less successful ones?
Yeah, the researchers also looked into things like system prompt modification, SPM, and model editing, ME. But these generally didn't work as well for causing harm, and often they just broke the model's usefulness. System prompt modification, it's a bit like trying that one magic phrase. It might work sometimes, but it's often brittle. Sometimes, using adversarial prompts like HEDA actually reduced harmfulness in Llama, or just made the model perform poorly overall, and model editing. It tends to be like playing whack-a-mole. You fix one bad behavior, but you might accidentally break through useful ones. It just doesn't seem very robust or scalable.
Okay, so these attacks during fine-tuning are a real threat. To fix it, researchers needed to understand why it happens. What were developers doing before to protect models? And what was the core problem they found?
Right. So traditionally, when you fine-tune a model, you're doing this delicate dance. You want it to learn the new task, but you definitely don't want it to forget its safety training. An early idea was bi-state optimization, BSO. The logic was, okay, let's alternate, train a bit on the safety data, then train a bit on the user's data, back and forth.
Okay, alternating makes intuitive sense. Reinforce safety, learn the task, repeat. Seems reasonable. So what was the flaw? Why didn't that fully solve it?
It sounds good, and yeah, the sources say BSO can help reduce harmful scores. But, and this is the really interesting part, researchers found a critical issue. If you don't spend enough time or computational effort on the alignment part, they called it asymmetrical computing, the model's safety can just plummet. Think about it. You might have a huge user data set you need to process, but maybe only limited resources for those safety checks. That imbalance is key.
And that imbalance leads to this excess drift you mentioned. The model literally drifts away from safety. That sounds like a fundamental instability.
That's exactly it. Excess drift is the core problem they identified. Imagine the model's knowledge, its weights, as a point moving around in this incredibly complex space as it learns. When you switch between optimizing for safety and optimizing for the user task, if you don't balance it right, especially if you skimp on the safety steps, that point can drift too far away from the safe zones. This causes convergence instability. The model essentially loses its safety bearings. It's like trying to steer a ship, but every time you adjust for the waves, your compass spins and you end up further off course from your safe harbor. It really is an instability issue.
So if excess drift is the culprit, the big question is how do you stop it? What's the clever fix the researchers came up with?
To tackle this drift problem directly, they proposed something called lazy safety alignment, or LISA, L-I-S-A. LISA refines that bi-state optimization idea, but it adds a crucial new ingredient, a proximal term, during the optimization for each state.
A proximal term. Okay, sounds technical. What does that actually do inside the model? How does it stop the drift?
Think of the proximal term as like an elastic band or a gentle magnetic pull. It constantly encourages the model's weights to stay proximal or close to the last known safe configuration. So even when the model is working hard learning the user's task, this proximal term makes the optimization process lazy about drifting too far from safety. It keeps pulling back. It's like having that co-pilot who's always gently nudging the plane back on the safest flight path, even while the main pilot is focused on reaching the destination quickly.
Okay, that makes sense. So the big question, does it actually work in practice? What were the results?
The results were actually very promising, quite striking according to the research. LISA significantly boosts alignment performance. In their experiments, models trained using LISA, especially with a stronger proximal intensity, a stronger pullback to safety, were much better at controlling alignment loss while still learning the fine-tuning task well. You can see the internal math settling down nicely, indicating stable optimization. It really does diminish that harmful excess drift. And what that means in practice is that LISA helps models say no to harmful requests, like how to steal a car, even if they were fine-tuned on data that included some harmful examples. Other methods often failed in those scenarios.
That sounds like a really significant improvement for anyone actually deploying these models. Is there a cost? Does it slow things down a lot or need way more computing power?
There is a small trade-off, but it seems manageable. LISA adds a bit of computational overhead, about 8.3% more clock time compared to standard fine-tuning. And it uses a little more GPU memory, around 3.14 gigabytes extra. But importantly, this overhead doesn't really scale up with the size of the training data, so it's not seen as a major bottleneck. The safety benefits seem to strongly outweigh this modest cost. And connecting it back, Lisa's success really underscores that you need this kind of multi-pronged approach, the alternating states, plus active drift control for robust safety.
Lisa sounds great for building safety during fine-tuning. But what about other situations? What if a model is already compromised, or if you want extra layers of defense? Are there other strategies?
Yes, definitely. People have explored other defense mechanisms, but they often come with their own challenges. One obvious idea is using safety data filters. Try to catch and remove harmful stuff from the dataset before you even start fine-tuning. Companies use tools like OpenAI's Moderation API, Llama Guard, things like that.
That makes total sense. Filter out the bad stuff up front. Seems like the first thing you'd try, but I guess it's not perfect. What's the catch there?
Exactly. The research shows these filters are generally pretty good at identifying safe data. They often get that right over 90% of the time. But their ability to reliably detect unsafe data is much more variable and often not good enough. Harmful content keeps evolving. Attackers get sneakier. The crucial problem is false negatives, the harmful data that slips through the filter. Even a small amount of that can be enough to launch a pretty effective misalignment attack. So filtering is useful, necessary even, but you can't rely on it as your only line of defense. Another approach people try is detoxification. This is about trying to erase problematic knowledge after the model has learned it, using methods like DNM or SOL.
Right, trying to clean up the model after the fact. Can you actually scrub the bad parts out effectively? Is it like updating software?
You can, to some extent. These methods often do reduce measurable toxicity, but there's usually a significant downside. They frequently hurt the model's overall usefulness, its utility. It's like you might remove the problematic knowledge, but you also damage its ability to do other things well. And maybe, more importantly, these detoxified models often aren't very resilient against new attacks, especially those SFT attacks we talked about. You clean it up, but it can easily get dirty again. It's often not a lasting fix.
Okay, so filtering isn't foolproof. Detoxification can hurt performance and isn't always robust. That brings us back to needing better solutions, especially for recovery. What's a more promising way to fix a model that's already been misaligned?
This is where another really novel solution from the research comes in: self-supervised representation defense, or SSRD. Just like SSRD was a self-supervised attack, SSRD is a self-supervised defense. And the big deal here is that it can realign a model without needing a big data set of explicit harmful content examples for retraining.
A self-supervised defense. That sounds potentially much more efficient, not needing all those labeled harmful examples. How well does it actually work?
According to the research, it achieves excellent realignment performance. It's very effective at restoring safety and doing so while maintaining the model's general usefulness, its utility. For instance, they took a llama model that had been badly misaligned by an attack and used SSRD to bring its attack success rate back down to zero. Zero. And it did this with only a tiny drop in the model's overall utility, around 2.9%. But here's the kicker, the efficiency part. SSRD achieved this using only about 50 harmful instructions just to generate the internal representations it needed. Compare that to standard realignment methods that might need 1,000 labeled samples. That's a massive difference in data requirement.
Wow, 50 versus 1,000. That's a huge efficiency gain. And what about resilience? You mentioned models can be attacked repeatedly. How does SSRD hold up in that kind of scenario?
That's a really practical concern for anyone running these services. The researchers tested exactly that. They simulated multiple rounds of attack, then realignment with SSRD, then another attack, and so on. They found that SSRD consistently brought the model back into alignment each time, while still preserving most of its utility. This makes it look like a really promising remedial defense mechanism, something service providers could use to reliably fix models after attacks without crippling their performance over time.
Okay, this whole deep dive really paints a picture of this constant push and pull, doesn't it? Making LLMs powerful versus keeping them safe. If you had to boil it down, what's the big takeaway for someone just trying to get a handle on the safety of these incredibly complex systems?
I think the biggest takeaway is just how fragile this safety alignment can be. We see models from different labs, Llama, Beaver, Mistral. They start with different levels of safety built in, but they're all susceptible to these kinds of attacks. Even models like Llama, which might have really strong safety guardrails initially, can still be broken, sometimes quite easily, through targeted fine-tuning. It's not a solved problem by any means. And what that tells us is that securing LLMs against harmful fine-tuning requires ongoing innovation, constantly thinking about both new attack vectors and new defense strategies. Solutions like Lisa, tackling the fundamental math of the optimization process to prevent drift, and SSRD, offering this efficient way to recover alignment. These are really crucial steps. They show we need sophisticated, multi-layered approaches to make sure these powerful tools actually serve human values reliably.
So we've journeyed through this really complex landscape of LLM safety. We've seen these potent attacks like SFT and the sneaky SSRA, but also these really innovative defenses like Lisa and SSRD. It's crystal clear that building safe AI isn't a one-time checklist item. It's this dynamic, ongoing process requiring constant effort and new ideas. It really makes you think, though, doesn't it? As these models get woven deeper into our lives, handling sensitive tasks, making decisions. How much responsibility falls on the developers to anticipate every single way things could go wrong? And how much do the rest of us as users need to understand about these vulnerabilities to even know what questions to ask about the AI we interact with daily?
That's exactly the question. What does it mean for the future if tools this powerful can potentially be turned against us, sometimes quite subtly? How far do we need to push to ensure true alignment with broad human values, not just alignment with whatever data was used in the last fine-tuning run, potentially malicious or not? It's a conversation we absolutely need to keep having, involving everyone from the tech labs to policymakers to, well, all of us.